Hi guys, welcome to this page of the notes, and now here's what we're going to do. So far we have looked at a couple of very unique characteristics of graphing rational functions: vertical asymptotes, horizontal asymptotes, and x-intercepts. Now what we're going to do here on this page is introduce you to two more characteristics that will sometimes show up in graphs of rational functions. The first one being oblique asymptotes. Now, we've been talking about these as we've been going through this set of notes. Remember, an oblique asymptote is simply a slanted asymptote, and there's really not a whole lot I can say about this except this. In order to find those slanted asymptotes, which you will need to be able to do, well, you can read it right here. The way you do that: synthetic or long division. That goes back to chapter 5 when we were finding or dividing polynomials. You divide polynomials by doing long or synthetic division, and I'll review with you how you do all of that when we do some example problems. So for now, I'm just going to leave it at that. Rule number one, there is no horizontal asymptote because you have a slanted asymptote. And the way you find that slanted asymptote is you divide the top by the bottom. That is a polynomial divided by a polynomial, and you'll need to do either long or synthetic division, and I will remind you how to do both of those when we take a look at some example problems. So we have x-intercepts, vertical asymptotes, horizontal asymptotes. If there's no horizontal asymptote, it'll be a slanted asymptote, and you can find that by doing long or synthetic division. And then the last little kind of characteristic that you might come across, number 5, is point discontinuity. So let's talk about point discontinuity. Point discontinuity is a fancy way of saying there is a hole in the graph. There's a hole in the graph. Now, again, let me say this. For those of you taking this class with me, all right, your graphing calculator will be zero help when it comes to finding these holes because of the pixelization in your calculator screen. When you graph these functions on a graphing calculator, you will not see the hole in the graph. It'll look like the graph is continuous. The only way the graphing calculator would be able to show you the hole is if you were to zoom in on the area where the hole is at. But you wouldn't know that just looking at it. It would look like a continuous graph. And the only way that you would be able to find these holes in the graph is by doing the algebra. So once again, yet another reason why, if you're taking this class with me, I don't want you to rely too heavily on your graphing calculator. Yeah, your graphing calculator knows that the hole is there, but it just can't show it to you because of the limitations of your graphing device, mainly the pixels in the screen. You can't fill in half a pixel. It either fills in the whole pixel or it doesn't fill it in at all. And depending on where you've zoomed, it probably won't be able to show you the hole. And the only way you're going to be able to find it is by doing the algebra. So let's talk about how you do that algebra for finding a hole in the graph, because your calculator most cases won't show you the hole in the graph. It knows it's there, it's just because of the limitations of the graphing device, it won't be able to show it to you. So here we go. Next page, let's take a look at point discontinuity. Let's say, for example, I have given you this rational function. All right, here we go. What I'm going to do to kind of describe point discontinuity to you is we're going to start by factoring this rational function. So here we go. Let's jump right into it. Let's factor this rational function. All right, take a look at the polynomial on the top, and I notice right away 3, 12, and 15. I can pull out a GCF of 3. I pull out a GCF of 3, that leaves me with an x squared minus 4x minus 5. In the bottom, there is no GCF to pull out, and so I'm just going to leave it as x squared minus 3x minus 10. Now, in my next step, right, this is now a general trinomial, and this is a general trinomial. Hopefully, it'll factor into two binomials fairly easily. Let's find out. Top and the bottom. All right, the easy bit. I need two things that multiply to an x squared. That, of course, would be an x and an x. I then need two numbers that multiply to -5, sum to -4. Well, that would be a -5 and a +1. So +1 -5. Okay, in the bottom. All right, the easy bit. I need two things that multiply to an x squared, which of course would be an x and an x. Maybe the slightly trickier bit, I don't know, let's find out. I need two numbers that multiply to -10, sum to a -3. Well, it probably, hopefully won't take you too long to figure out that a -5 and a +2 will do it. So +2 -5. And here's hopefully what you recognize. I have the same factor in both the top and the bottom. X -5, x -5. Now, in section 1 of this chapter, what we would have done is we would have said, oh, those factors cancel each other out, and reduced this rational function down to just this guy, 3 times x plus 1 over x plus 2. We're not going to do that in this case, because when graphing these rational expressions, I won't actually ask you to factor the top and bottom and simplify. We don't have to worry about doing any of that. But I do want to show you how this idea right here will show up, and why on a graph it'll show up as a hole in the graph. All right? So here we go. Stick with me for just a second. You're going to love this. I have three different factors. I have an x plus 1, I have an x plus 2, and I have an x minus 5 that shows up twice. Now, how will those factors become zeros? Well, the x plus 1 would be a 0 if I plugged in what? Yeah, x equals -1. So, let's do that. Let me come right up here, do a little bit of work for you guys real quick. If I let x be equal to a -1, here's what happens. Then, f of x, which is equal to 3 times x plus 1, x minus 5, all over x plus 2. X plus 2, x minus 5. Here we go. Let's plug that stuff in, right? If I plug in a -1 here, that's going to become a 0. So I would have 3 times 0. If I plug in a -1 minus 5 would be a -6. So that gets me -6. In the bottom, -1 plus 2 would be 1. And -1 minus 5, again, I get a -6. Now, go ahead and put all that stuff together. Here's what you wind up with. 0 times anything is 0. So I wind up with 0 over 1 times a -6 is -6. Now, guys, what happens when the numerator is 0? Well, we just looked at several example problems graphing where this happened. You set the numerator equal to 0, and what do you get? Yeah, you get x-intercepts. So this guy right here, when x is equal to a -1, is an x-intercept. Right? We have an x-intercept. So we would have an x-intercept at x equals -1 because that gives me 0 in the top. All right, stick with me. Right here. The factors, we just did the x plus 1, we said -1 gives me a 0. My other factor is x plus 2. What would make that factor 0? Well, if x were a -2. Okay, let's do that. Let's make x a -2. Then f of x would be equal to 3x plus 1, x minus 5, all over x plus 2, x minus 5, equals, Here we go. I plug this stuff in. 3 would just stay a 3. If I plugged in a -2, let me fix my 3, that looked ugly. All right, if I plugged in a -2, -2 plus 1, -1. Okay, -2 minus 5, -7. Keep going. In the bottom, -2 plus 2, that's a 0. Okay, keep going. -2 minus 5. Well, again, that's a -7. All right, guys, what does that come out to? Well, -1 times a -7 is 7, and 7 times 3 is 21. In the bottom, 0 times anything is 0. Well, hang on a second, guys. What happens on a graph? What happens when 0 is in the denominator? Well, when 0 is in the denominator, you know that it's division by 0, which is undefined, and on a graph shows up as a vertical asymptote. So when x is equal to a -2, you will have a vertical asymptote. All right, and all of that came from this guy right over here. Slide that out of the way, slide that out of the way. This guy right here where we did, right? I did -1 because that makes that factor 0. We did -2 because it makes that factor 0. One more factor. What if x was a +5? Now this one's really important, right? We just looked at x-intercepts. We just saw vertical asymptotes. But you say, well, I thought we were talking about point discontinuity. You bet we are. Here we go. If x is equal to 5, then f of x, which is 3, x plus 1, x minus 5, all over x plus 2, x minus 5. I plug in a +5, and here's what I get. The 3 stays a 3. 5 plus 1 is 6. 5 minus 5 is 0. In the bottom, 5 plus 2, 7. 5 minus 5 is 0. Check this out, guys. I have a 0 on the top. 3 times 6, 18. 18 times 0 is 0. In the bottom, 7 times 0 is 0. And look what happened. I wind up with 0 over 0. So when I plugged in, when I plugged in a -1, I got a 0 in the top. 0 in the numerator is an x-intercept. When I plugged in a -2, I got 0 in the denominator. And 0 in the denominator is a vertical asymptote. When I plugged in a +5, I get 0 in both the top and I get 0 in the bottom. And guess what that's going to be? You bet x equals 5 is going to be what we'll call PD, point discontinuity. Point discontinuity, 0 over 0. And guys, what we call this is the indeterminate form, 0 over 0. What it means is this function does not exist when x is equal to 5. 0 over 0 does not exist, and on a graph, that will show up as a hole. Just the graph ceases to exist when x is equal to 5. So that's why there's a hole in the graph. It exists everywhere else. Pick any value of x you want to, you'll get some function value. Y will be equal to something. But when you plug in x equals 5, you get nothing. You get this indeterminate form, 0 over 0. The function doesn't exist, and that shows up as a hole in the graph. There just is no function. It doesn't exist. So watch out for this 0 over 0, and it will occur anywhere you have the same factor in both the top and the bottom. Guys, we will practice this idea a whole bunch more in a couple of example problems. So head on over to the next page of the notes, and I'll meet you guys there.